So this tells you how you can, from Microsoft, how you view the cloud. It is basically an extends your desktop. They've done a lot of work in that direction. Things like making Excel stretch from your desktop to your cloud. We've already pointed out the cloud as a backend for storage is pretty useful for backup. We can use it for collaboration. All the collaboration systems tend to be built around clouds because you want to share, because collaboration is sharing things. SharePoint is IBM's collaboration environment, and Sakai is an open source university environment for collaborating. We have a Google App Engine and Office Live, which are examples of applications running directly on a cloud. For example, you can now run Windows Office either on the cloud or on your laptop. And here's an example of sort of the hybrid cloud or cloud bursting, namely, one can take an Excel application and imagining it bursting to a cloud when it gets too big for your desktop. Same with MATLAB. When it's chunking along with a few images, it runs on your laptop and then it bursts to the cloud to do a large problem. So that's a pretty reasonable model. It's all to do with cloud bursting and possibly formulated as a hybrid cloud. Exactly how you formulate it is not clear, but the view of the cloud as a magnifier for your desktop is, I think, a pretty good model. Here is a Microsoft view of what a cloud has. It is a shared facility, so we're getting economy of scale by sharing our facility among many people. We have automatic deployment and management of virtual machine instances. You just ask for an instant and it gets created for you. And we can go up from 1 image to 10 or 1,000 images. So that's elasticity or dynamic scalability. We have tremendously good fault tolerance. There's actually a slight flip side there, namely clouds tend to be more prone to fault than traditional machines. Systems because they're not actually aimed to run, they're aimed to scale, not to be have nodes that are individually fault tolerant. And so you actually need to worry a little more about fault tolerance running on a cloud than you do running on a traditional, highly robust central system. We have the replication of data, things like the Hadoop file system or the Google file system, automatically replicate data multiple times. You can choose the exact level from 1 time, which is non-replicated, through, say, 6 times, which is highly reliable. And you can either have, these are the different forms of parallelism. When you have run on a cloud, you have parallelism over users, and within the user, you have parallelism for a single task. So here is another view from another Microsoft view of what a cloud is. It has the illusion of infinite computing and infinite storage and everything delivered as a service. And we have customer data centers, collaborators data centers, and public data centers. This is this hybrid cloud linking different types of clouds together, not necessarily linking Amazon to Google, but linking, say, an OpenStack or equivalent private cloud to an Amazon cloud, because OpenStack can be linked, images can relatively easily be converted to Amazon images. We know how to construct them because OpenStack has an Amazon compatible interface. So this is all near-term cloud usage. And such clouds offer from NIST on-demand service. These are the same things we've seen. Network access, resources pulled between many users, a flexible way of allocating resources on demand, and most importantly, you only pay for what you use. You measure the service that you get, not the service that you thought you might get. And all of this is done in a fashion that has green IT, namely its economy of scale. It uses, economy of scale gives you good performance and also very efficient PUEs, the power usage. I'm forgetting now what the E is. PUE is the power usage coefficient, which is, if I remember rightly, 1.16 for Gmail, and that Gmail slide also said it was 2.5 for our small business operation. And we are able to use minimal electrical power because we've optimized our data center so it needs as little power as possible for non-essentials. And then we have these wonderful new software models such as platform as a service with MapReduce and NoSQL and software and database as a service instead of databases, an add-on to my job. So again, get a different view, another view of clouds. I deliberately have multiple views of clouds. So at the end of this, you'll believe some sort of amalgam of different people's points of view. So we have scalable, it's persistent. We don't worry about backing it up because it's intrinsically fault tolerant. It's outsourced, so we don't have to actually worry about managing it. We can use it for incredibly large data systems because the world's biggest data, search and things like that, and recommender systems that run on cloud. So obviously the world's largest data analysis is done on clouds today, and it amplifies our desktop experience. We can view the cloud as the back end, which we access seamlessly to get to do computations which are reported on our desktop. And it gives a modern data center architecture. I pointed out that although clouds can be thought of in terms of their functionality, you can view what people developed to actually address modern Web 2.0 social networking search sites. It is just the very best high quality, highly efficient data center architecture for large scale applications, where we actually do small scale applications by joining lots of small scale applications together in a public cloud. Here's another architectural picture, layered picture. We have our virtualized cloud sitting here, renting instances, using hypervisors. We're sitting here at our university, accessing the cloud, and then we have services which provide us our interfaces, and hopefully we do everything with a good data center architecture, and we do things well. So here's yet a different definition. Here we have the Microsoft Cloud Network in the USA, and pay-as-you-go, managed, scalable, reliable, on-demand applications. Here's some obvious examples we've seen: file storage, search, email, social networks. And if you're a startup, you just use the cloud. You no longer have to worry that you spend too much money or too little money. If you're a huge success, your worry is too little money. And if you're more typically not so successful, then you worry about spending too much money, and you have no upfront capital costs. Here's some mythologies, which comes from this tutorial that cloud computing. So this is what the cloud isn't, or isn't just. Cloud computing infrastructure is just a web service interface to operating system virtualization, so that if I run Zen in my data center, I'm running a private cloud. Clouds and grids are equivalent. And another mythology is the clouds impose a significant performance penalty over so-called bare metal, namely non-virtualization. Now, all of these mythologies are actually a little controversial. Clouds and grids do have a lot in similarity, and clouds and utility computing, which grids were addressing, are pretty similar. And there are some applications where cloud computing does have significant performance penalty. And of course, clouds do support services, and they do have operating system virtualization. They just have a lot more. So now this points out, this slide, the things we've seen before. The cloud is an integrating point for phones, laptops, all our local TV and our computing surface and our media wall. And of course, the smart home and the smart house and the smart city and our voice and our gestures analyzed locally and sent off to the cloud will all be integrated together in this new world where we have lightweight clients, tablets, and smartphones, with clouds providing all the back-end intelligence. So yet another view of the history of the cloud. We started off with the Web 2.0 applications. Then there was the challenge of doing hundreds of millions of email users searching in this enormous number of photos. Is now 500 million a day uploaded. Incredible number of web searches, indexing the entire web. And that challenge was met, and that produced big data centers. And this magic number of 0.15 seconds is how long a cloud must not take longer than this to respond to your search request, because otherwise it's been shown the user gets miserable. And miserable users are users who leave your website, and then you go bankrupt. So there's huge commercial incentive to provide quality performance and in your cloud, and that is meant to, that's why companies are ahead of academia. Academia doesn't have quite the same killer need to succeed in tomorrow or today or yesterday, and so it's academia moves rather slower. This defines some concepts here. The public cloud, that's Amazon, which is a large-scale infrastructure available to rent. It virtualizes everything. We isolate the different tenants, even though the infrastructure is shared. You can still worry about security breaches, and there are many papers studying this. The counting is done in a typical web-based transactional fashion. We have dedicated resources in the private cloud, and you can just you can use cloud technologies, but just private, and you may be the only user, and you may actually dispense with some of the features, the rental type features that you have on public clouds. Then we have a cloud running actually on our premise. Then they're not a public cloud, but we run a local facility in a similar fashion to a public cloud. So if you want to know how to do this for a public infrastructure as a service, we need Zen and KVM to provide the CPU isolation. That's the so-called hypervisor. Then we do some networking provisioning to give you network isolation. Then we actually have things like OpenStack and Eucalyptus to manage this. We have service level agreements which tell the customer what they're going to get for what they pay for. And then we have services that are accessed by the web to get the computing by web interfaces. And then everything is e-commerce based. You just take your credit card and buy what you want.